Right. Welcome back, everyone. So in this final talk of the morning, Vadim will give finally a true board talk and will tell us about zero knowledge proofs from lattices. So Vadim has been doing great work on lattice-based crypto, and it's going to tell us about the state of the art.
Yeah, thanks, Stefano. Yeah, so I'm giving a board talk, and I mean, the reason I think that, a lot of these tools keep getting reused. So I think it's easier to keep pointing back at them to not erase stuff than to keep coming back. So I don't know. That's the theory of it. It's echoey. Okay. So this talk is about lattice-based zero knowledge, and it's not just it's not just can we do lattice-based zero knowledge, prove sort of lattice pre-images for lattice, the width for lattice witnesses in zero knowledge. Of course we can. Right. I mean, there's nothing special about that. The question is, can we do it efficiently? Right. So, I mean, the goal at the end is to build privacy-based protocols based on the hardness of lattices. And the reason we want to do that is, you have to give motivation for this, because we can build privacy-based protocols based on just hash functions. I mean, you have all these great schemes like Aurora, Ligero, whatever. And that's, I think I'm showing my age because he's like 5 years old, which is a lifetime in zero knowledge. There's probably a plus in front of all of them. And they're already quite efficient. They're actually even snark, so they're compact. But the point is, the hope is that by sort of leveraging the algebraic structure of lattices, you can do the same thing much more efficiently, right, and more compactly. This is kind of the state of the art, the same as the state of the art of digital signatures. You can get digital signatures, even quantum-safe digital signatures. I think these were the first digital signatures that were ever invented. There were quantum-safe digital signatures from Merkle trees, right? But with specialized assumptions, whether from lattices, from other stuff, you can get them more efficiently, right? So this is kind of the same hope as with zero knowledge. But the interesting thing about zero knowledge is that we're talking about replacing Aurora, Ligero, but we can't even do Schnorr efficiently for that. We can't even do Schnorr kind of efficiently for lattices. So forget snarks, forget compactness. Just you have AS equals T, prove that S is small, right? So this is the kind of the general thing. You have some matrix A, let's say mod Q. I'm not going to write mod too much. And then prove knowledge of S and norm of S is small, right? So can we even do that, right? So you would think that the very first thing you should be able to do, if you talk about zero knowledge, is to prove the basic one-way function, knowledge of basic one-way function, right? And even this we could not do efficiently. I mean, of course you could do it, and the best schemes were kind of took a couple of megabytes to prove the basic thing, but this is not acceptable, right? Because I don't know, Aurora, Ligero, I mean, they can do it in a few hundred kilobytes. They can do anything in a few hundred kilobytes, right? So then, I think it's a very good question as to why. Why is it so hard? For discrete log, it's very easy. This protocol existed for a while. It's Schnorr. So what is the difficulty with lattices? And I think the fundamental difficulty is, well, it's the small part, right? And because when you say small, that's a range proof. And if you know things about range proofs, they're not trivial to get. They, usually the most efficient ones have these, yeah?
Just the basic one. Is A short and fat, tall and skinny? What is A?
Well, it's not tall, right? It makes the problem hard. Otherwise,
okay.
There's no error. I'm never going to write an error. This is LWE. If you want error, put an identity in A. And, yeah, I mean, it kind of doesn't matter. So, yeah. Okay. So the hard part is the small, right? Because it's a range proof, and range proofs are not easy, right? So now we're kind of, so the goal of this whole line of research is to get range proofs for, from lattices. And I think in the last couple of years, we really went down from like 2 megabytes for the most basic thing, and now we're down to really 10 kilobytes or something like that. So, and it's, so what I want to just talk about today is just kind of a toolbox for, for how to do these things. And it turns out it's actually quite simple. So if you kind of, I don't know, walk away from the talk thinking the whole all the people are incompetent in this research area, I think I will have done my job. So yeah, because it really is, the toolbox is quite it's quite small, maybe. Yeah.
Can you remind us what Ligero is? Like, what does it do? Is it a succinct, square root succinct? The
square root, yeah, square root succinct doesn't even matter, right? The point is that
it's based on general assumptions.
It's based on hash functions, right? And so there's always a target to beat. You can't just say, no, public key encryption. You say, I have a lattice-based encryption scheme. Well, live with it, right? Whereas here, you have to say, no, look, how does it compare to the generic source, right? So you don't want to make lattice assumptions unless they are useful for some,
of course,
right?
And the way you would use Ligero here is write down the verification circuit. And
exactly, I would just commit to S using some hash function and prove that S, I know the committing to S and S satisfies. And this is what we're going to do for lattices as well. We're going to commit to S and then prove that S satisfies this relation.
Yeah, so the question on this is exactly, so what are the rules of the game you're playing, right? So because you can compile it as an empty statement in any other chip system, but you want to have something more latticey, I guess.
No, right. No, there are no rules to this game, right? So it's not that we're saying, no, Ligero is out, because that, no, the rule is you want to minimize the proof size.
Efficiency, that's it.
Just the proof size, right?
Proof size. Yeah.
And here I'm going to talk about just linear proofs. So nothing compact. So even that was hard, but compact, that will, you first have to get linear proofs. So that's what.
Improving the proof size comes with corresponding improvement to the running time, to the prover's running time, verifier's running time, or there is some trade-off?
Right now, everything is linear or linear or quasi-linear in terms of the witness limits. So there's even that was a hard. I mean, linear. You can always define efficient. You can always redefine efficient, right?
From complete efficiency, it's not that you're paying any price if you make the proofs as short as possible. It's not like it's making the proof work harder or something.
I mean, maybe it's maybe some small factor harder, but it is there's no tricks. There's nothing bad that will happen. I'm pretty sure it's going to be extremely efficient. We have implemented versions of this, and this is kind of along those lines, so it shouldn't be. So yeah. So since I don't have slides, if you want to go back, kind of get you want to kind of get some background material for this talk. I'm kind of summarizing this the introduction to our paper, which is so it's an ePrint 2000. So it's a crypto, but it's an ePrint like 2022-284 ePrint. If you want to kind of get the slides or some written material for it, it's this. So it's joint work with my students, Can Nguyen and Maxime Planson. But it's actually based on work that was done, by before as well. So all the references you can get in that paper. Okay, so let's first, we want to try to do Schnorr. Let's see what happens if we try to do Schnorr. Okay, and so I'm going to say that we're going to prove this equation we're trying to prove. I want to prove it. I want to be able to prove it. I don't care if it's over Z, over some polynomial ring. This doesn't matter. But we are going to want to, like I kind of hinted, we're going to want to commit to S and then prove this relation. And the commitments are going to be most efficient in polynomial rings. And so I'm going to kind of define this ring, RQ, forever, for the remainder of the talk. It'll be sort of this ring, ZQX mod X to the D plus 1, where D is some dimension. So this will be, we will be basing everything on module LWE. And we'll get into it once the thing starts. We'll know what module LWE is. Okay. So I mean, if you've heard of ring LWE, this is kind of the same thing, except the rings are smaller and there's more of them. But anyway, yeah. So we'll get into that. Doesn't really matter. So there's D. Again, I will try to motivate why we set everything the way we do. But I do want to kind of hint that module LWE is really the right problem to use. It's not for security. It's really the kind of the right thing to do, and hopefully you will see why. Okay, so let's say we have AS equals T mod Q, and everything is over this ring. All the elements in A are over this ring. Okay, and if you have questions, just ask. I mean, that's kind of yeah. What's the value of D? So typically, so we'll see what it should, but typically it'll be 64 or 128. Sorry. So let's say Q will be about let's say 2 to the 16, 2 to the 32, and D will be about 64. And so we have the matrix A. Okay. So here's the A. Maybe I use a different color. This one is down. So here's your A. And it's it's this n by m matrix. And the hardness of the, the dimension, the integer dimension is d times n and d times m. Right? It's kind of the hardness of the sys problem depends on that. Okay. All right, good. So let's just try to do a basic protocol to try to prove this, to prove that we know a small s, so let's do Schnorr, okay? So we pick some y, some masking parameter y from some distribution, so make it small, then compute w equals ay. Mod q. Okay, so then we send w. The verifier, so this is the prover, this is the verifier, picks a challenge C from some challenge set, sends C. I will kind of try to define a little bit what these are. He computes z equals sc plus y, sends. And then the homomorphic relation that's going to be satisfied is az equals tc plus w. Okay. So if you've seen Schnorr, this is Schnorr, right? But there are some things that are different to lattices. In Schnorr, y is uniformly random. So y completely masks SC. For lattices, that's not really interesting because you want z to be small. Right. So the whole hardness of lattices is smallness, right? So something has to be small. So if y is not big and y is not uniform, then it doesn't quite mask s times c. So that's a problem that could leak s. So you have to do some rejection sampling here, and I'm not going to talk about this because this is pretty old already. So you have to kind of do some rejection sampling to make sure that the distribution of z is going to be uniform in distribution of s. It is going to be independent in distribution of s. Okay, I'm not going to. This is let's say sort of standard by now. And so now this C, right? You want the challenge space to be big, right? So this is kind of why we want this ring to be somewhat big. So what we want is we want the challenge space to be big, but at the same time, Z to have small norm, right? So if C is an integer, well, you can't really have that many small integers, right? So that's why it's nicer to have C be a polynomial, and then you have a lot of small polynomials. If it's a polynomial of degree 64, well, there's 2 to the 64, 0, 1 polynomials. And
so you want C to be large to avoid parallel repetition, or
I want the size of the challenge space to be big, so you don't do it Europe. So you have soundness, but I also want the norm of C to be small, so that you have Z being small. Okay. Yeah.
what's the norm for the C? It's just the norm of the coefficient.
Yeah, norm of the coefficient.
Yes. For the rejection sampling, you have to start over, or
if you reject, you have to start over.
it's not a problem to reveal you rejected.
It's not a problem for what?
To reveal that you rejected.
Okay, so this is a good question, right? So in an interactive protocol, you can prove that if you don't reject, right, then actually the distribution is perfect, right? In an interactive, if you do reject, then not quite. So so there's two answers to this. One is you can easily make everything zero knowledge by hashing the W. But actually you don't care, because I don't even care about interactive protocols. I care about non-interactive protocols, and there you never really reveal that you reject it, because you just keep doing it until you.
You mean like if you do Fiat Shamir, then
it
doesn't matter.
That it doesn't matter because you never see any rejected transcripts. But yeah, this is something that I'm not. But yeah, but sure, you should ask questions about kind of this stuff as well. But I'm kind of not covering even how to do the rejection sampling. What's the most efficient way to do it? Okay, so now, so what does this really prove, right? What did we end up proving? So the way you, yeah. I'm sorry. No, C is not. C is a subset of RQ that has small coefficients.
Okay, C is a subset. And then what is the computation for Z?
Is S times C.
S is a vector.
is a polynomial vector. So you multiply a polynomial vector times C.
So that the quotation happens over RQ.
Everything happens over RQ.
Everything happens over RQ.
But there's no reduction mod Q here because they're all very small. S is small, C is small, Y is small.
So A is also elements in A is also elements in RQ.
Yeah, everything's in RQ.
Oh, okay.
So good. So now, what does this prove, right? Why does this not prove this? For Schnorr, it proves what we want. Here, it does not. Well, it's because, so let's just do the basic thing. Let's do rewinding, right? Let's extract something. So, okay, so let's C Z, right? So he rewinds C prime Z prime, and we know that AZ equals TC plus W, and AZ prime equals TC prime plus W, right? And norm of Z and norm of Z prime are small. Okay, so from here, what he gets is he gets A times Z minus Z prime equals T times C minus C prime. And I'm just going to rewrite this as like A times Z equals TC. Okay, so this is what we extract. So in Schnorr, so when something like this happens, you just divide by C. Here, not so much, right? Once you divide by C, now things are not small anymore, right? But it's okay, right? Because you do prove this. And so basically knowing an S satisfying AS equals T, you end up proving a small Z, which is not as small as S anymore, right? Because we multiplied by C, we added some Y, so now it's bigger. And there's this C that's appearing. It's small, but it's still not what we want, not what we know. We know something more, but we can only prove this. Okay?
So is it good enough though for applications?
Yeah.
You would use this to prove to NP, zero knowledge for NP somehow, right? Is that good enough?
So this will be, yeah, I mean, this is kind of what we're building at, right? This will be good enough for, so this is not what we want, but eventually, but this is all we know how to do. So we will use this to build what we want, okay? All right.
Why does having this equation proves that you know S?
No, it doesn't.
Now what? I get them at an even more basic level, yeah.
So all I proved is that I know a Z and a C satisfying this equation.
Oh, okay.
That's all I proved. Right. So this is not what we want. Right. If I then, so what I'm building at, at this talk is to prove this. So far, we have this. Right. Okay. But you should believe that this is still hard, right? If I give you A and T, it's still hard to come up with a Z and a C satisfying this. This is as hard as cis, somewhat easier version of cis. I mean, the proof is simple, right? I mean, if I know A and a T, so I can basically set up A and AS equals T, right? The solver gives me a Z and a C. So AZ equals TC, right? And I just plug in the S in here. And so from this, I end up with AZ minus SC equals 0, right? And so I have a solution for cis. You have to be a little careful. This can't be 0, right? So why can't this be 0? Or at least why isn't it 0?
Many to one.
Many to one, right? I pick my S so that there's many S's that there has to be at least 2, right? I just pick it so there's 2, and then with probability at least a half, this will not be 0. Okay. So this is still a hard problem, and this is basically used as the basis for a signature schemes, for example, right? So I just proved I do this, right? And the hash in the Fiat-Shamir, the message goes into the hash, and this is a signature scheme. Because if you can forge, you can solve this problem, which is as hard as this. Okay. So for signatures, this is all we need, but this is not quite good enough for other things. For example, this equation could also be an encryption, right? Like the reg of encryption has this form, AS equals T, right? So if I want to prove to you that I encrypted correctly, this doesn't quite prove that, right? Because I say, look, I encrypted correctly. Well, not really, right? Maybe you multiply by C, and now the decryptor can't even decrypt. Right, so that's one of these applications that you sometimes want, right? You want to prove that, hey, anyone can decrypt. The guy with the secret key can decrypt, but he cannot because there's a C. Yeah.
Is it clear there's actually like an attack, like that it suffices just to know how to do this weaker thing? Like, it's not clear to me how to do this weaker thing without, or how to actually run the protocol successfully without, how to actually prove successfully without actually knowing.
Why not?
No, so this is a good question, right? I mean, for example, you could come up with artificial ways, right? I could give you, for example, let's say I'm hoping that C is a factor of
Right.
something.
But that's not a reasonable hope.
But let's say I give you an S where S is perturbed a little bit and only sometimes you know how to. But there's a so I see what you're. So Noah's question is, but really, if you do this, surely you know the S, right? That's kind of what.
Yeah, it's like a flaw in the definition of proof of knowledge as opposed to.
But
Is that sure?
so no. So I don't think that's even if that is correct, which I don't think it is, which it's not. But no. The point is this. That's not good enough because, like, I'm going back to my encryption example, right? Let's say I encrypt something. I want to prove that I encrypted correctly, which implies that you can decrypt, right? Okay, but I could be cheating, right? I could have, divided my S by like, x-1, for example, and then I'm hoping that the C you get will be a factor of x-1. Then I divide out, and the point is, even though yes, I know the S. Right? It's not a valid encryption anymore, right? So basically, I cheated in the kind of the statement is false, right? And that usually you want the statement to be true for applications, right? Otherwise, it's kind of pointless. Okay. All right. So yeah.
So this is a literal translation of Schnorr, right? And trying to prove something about it. Is there a sort of different way, let's say multiplicative way or something? So instead of additively translating S, right? Multiply S by rotate S, randomly rotate S, let's say.
I mean, like an automorphism. I mean, we've thought about all these things.
Yeah.
And the group is additive, right? So it's not, there's this, the homomorphism is this way. So, and you also want your, the challenge space to be big. I mean, we've thought about, I mean, this is what took decades, but there's really, I mean, the strategy is you use this and then you commit, you can create a commitment. So that's the next thing I will show you. You can create a commitment scheme from this, and then you commit, and then you can prove stuff about the committedness. So this will be the thing, okay? So kind of what I'm gonna do, at least the outline is, so you prove AZ equals CT, right? So we have this. That's all we know how to do. So from this, we can get a commitment scheme. With a proof of opening, And then you can prove linear relations over RQ. So in the commitment scheme, I can prove to you that my, the committed values satisfy some relation of RQ. Now, the interesting part, so this is not super interesting, this is kind of easy. The interesting part starts in this step. Now I can prove linear relations over ZQ. Zero knowledge. So all this is zero knowledge. So when I say prove, it's proven zero knowledge. Okay. So this kind of, because now something is happening. And then even more somewhat interestingly, you can prove linear relations over Z. So not mod Q anymore.
So why is going from RQ to ZQ the hard or the interesting part?
Well, it's not super hard, but it's not. It's not. So you think it should be trivial?
Because you can embed ZQ inside RQ.
But you don't want to reveal the other parts.
Sorry.
You don't want to reveal the other parts. And you want to prove, yeah. So we will be embedding. And so none of this is going to be complex. So in retrospect, this is all, this is all going to be, so yeah, it's pretty simple, but yeah, I mean, we will want to embed relations in ZQ or RQ and then hide all the irrelevant, hide all the other parts. Not hard, but it has to be done. Okay. So then kind of using very similar kind of over here, we're going to do prove quadratic relations over RQ. The kind of the same techniques will be proving quadratic relations over ZQ. This will be the same idea. Once you have this and this idea, it's the same thing. And then you can prove quadratic relations over Z. And then once you can prove quadratic relations over Z, now you have norm, right? Squared norm, okay? But you can get exact norm here. Here, I'm going to show you can get approximate norm as well. But so you can get rid of the C, but the Z will still be bigger than the S. So kind of in this step, we will prove, given knowing AS equals T, I can prove that I know A times a bigger S equals T. And once I have this, then I can prove to you that I actually know the S of the exact norm that I.
But also, once you go into the right-hand side column, you are in NP land, right?
Yeah. Here you can do, yes. But again, efficient. We want to do things efficiently, right? So just a bunch of tricks to.
So it's more than sort of getting to the right-hand side column, writing down the verification equation here as a degree 2 polynomial, and then applying it. Is it?
Basically, yeah. It's going to be that. Yeah. Okay. So I'm going to do a small rewriting. Okay. So basically, so if you have AS equals T, we have AS equals T. I'm going to prove. So we can prove, like I said, AZ equals TC. But I'm going to rewrite this. This is equivalent to saying I know a V and a C such that AV equals T. Norm of C is small. And VC is small. It's the same thing. It's just more convenient. Do you see how? It's really just if you're awake type question. So knowing a small Z and Z bar and a C bar satisfying this is equivalent to knowing a V and a C satisfying this. What? Yes. Oh, I mean, it's easy, but there's one little issue.
Z equals VC.
Yeah.
Z equals VC. Yeah.
But not all Z's are of the form B times C, right?
So no, I'm not going up and down. Yeah, let's just go this way. Yeah, but wait, there's a okay. So V equals Z over C, right? Z bar over C bar, but this requires that C bar is invertible. Okay, so we need to kind of assume that and the C bar, remember, was the difference of these two C's. We have to kind of assume that the difference is invertible, which is not always true, but we can always set it up to be this way, and we don't pay any price. Okay.
You just take Q to be a prime such that
this no. So I mean, you're going to say you want this to be a field. This is never a field, except for D equals 2. Yeah. Actually, yeah, this is never a field. The best you can do is split into D over 2 parts, but it's okay because you can prove that small elements are invertible.
So I guess you pick a random small element, right? And then you have a very large set of other guys that you subtract from it that makes the difference invertible. Is that
Because, so for example, I mean, this could be easily false if this splits completely, right? If x equals 1 splits completely, then the probability 1/q, this will be not invertible. Well,
if you pick C and C prime random to be random small, independent random small, potentially.
Yeah, but that's what the prover can wait for, right? He can wait for C's that are, like he can sort of choose which C's he answers.
Okay.
You need to be special like with probability 1 or like just with overwhelming probability.
It would be, it's fine if it's with high probability over random C's, but and we thought we needed that because when we thought we wanted things to split, now we don't care. So we can really set it up. We can pick a Q that I think equals 5 mod 8 or 3 mod 8, and then it's all the small elements are inverted.
For some very special field.
When Q is 5 mod 8 or 3 mod 8, I forget which one, then all small elements are inverted, and that's good enough. Okay, all right. So now, as I'm sort of hinting, we're going to build a commitment scheme. And so I'm going to prove that for AT, if there exist two valid VV prime satisfying, 1, 2, and 3, then we can break this. Cis is broken for A. Okay, so A is always going to be some random, common random thing. So cis is broken for A. Okay, so this is also not so hard to see, right? So suppose we have A times V equals T and A times V prime equals T, right? We have this, and these C's exist. Right, some C and C prime exist. So do you see what happens, right? Then this implies that A times V C C prime minus V prime C C prime equals 0, right? Just by multiplying by C C prime on both sides, subtracting, right? And then you end up with this. Well, this is small. This is small, right? A small norm, that's by this assumption. And now multiplying by C prime and C is also small. That's by this assumption, right? So this guy is small. And it's not 0 because these are invertible and V and V prime are not the same. Okay.
So something I missed, probably crucial, right? V is not small norm.
V is not small. V is Z divided by C. Yeah. If V were small, then we'd be done with this, right? But V is not small.
Yeah.
Okay. All right. Good. So we have these things. So just something to remember until the next thing. So now we have commitments, and commitments we also already know. So far everything is simple. I'm just sort of setting it up for what's going to happen. All right. So now we have the Ite commitment. And this is basically when Ite invented cis, it's immediately a commitment. Okay. So you have a message S1, and it has small norm. So to commit to S, you pick randomness S2, small norm, and output A times A1 S1 plus A2 S2 equals T. Okay, so that's it. That's the commitment to S. Okay, I think everyone has seen this. Okay, and now I want to give a proof of knowledge. So the interesting thing is that we're going to be giving proofs of knowledge of openings, right? So I'm going to give a proof of knowledge that I know an opening to S1. Okay, and so all I do is this, right? That's the protocol. This is the only protocol we know, so we're going to use this protocol, right? So we're going to end up proving, right? So the A is like the combine. I mean, the A is A1, A2, and the S is S1, S2. And then I run this protocol. Okay, this is a bit, yeah. Okay, so what are we going to end up proving from this? Right, we're going to prove that we know A1V1 plus A2V2 equals TC. Equals T. Right, and then there's some C. There also exists a C satisfying that C is small, and this time C is small, this time C is small. Okay, and by this lemma, these guys are unique. Okay, there's no second opening. Okay, therefore, this is the message. Right, that's my message. This is the commitment.
Wait, sorry, can you remind me why is V1, V2 unique?
Sorry?
Why do you have uniqueness?
It's computationally, right? Okay, it's not.
Yeah, based on
Oh, yeah.
cis.
Oh,
Based on cis.
Right. I see.
Okay, so it's binding, and the hiding part comes from the fact that A2S2 is pseudorandom. So that's it. This is the Ite commitment with an opening. Okay, and now what if I want to prove a linear relation over RQ? Right? Let's say I want to prove that. Let's suppose we have R times S1 plus R equals 0. I want to prove that this is satisfied. So with this commitment, it's trivial as well. So you just write. So then you have these equations are satisfied. So you have A1S1 plus A2S2 equals T, and also negative R 0. Yep. So this is the equation that is satisfied. So all you do is you set up this, and then you end up proving this one. And this implies that this linear relation over RQ holds. So nothing really happened. And the important thing is that the proof size is the same. Because the proof size only depends on the size of S1. So it doesn't depend on how tall this matrix is, it just depends on this. And of course, you do more work, but the proof. All right. Good. All right. So now just a small thing. The Ite commitment is great. It's fine. It's actually really good because if the S1 is really tall, is really big, the commitment is still small. So the commitment size does not depend on the message size, which is good. But the norm of S1 has to be small, right? So we also want to be able to. We want a slightly different commitment that can commit to bigger messages, right? To sort of messages that are arbitrary RQ, right? So this is like also kind of simple for this BDLP commitment. So there, to commit to M, so M, we would write A B R plus 0M equals. Now R is small. This is the randomness. Okay. Yes. All right. Good. So and M can be arbitrary. And the way you prove that you know M is you just prove you know R, because the R determines the M. Okay, because M is just TB minus BR. So and the R is going to be unique by that. So nothing is happening. It's just now we have a way to commit to M. And it's so binding by cis, hiding by the fact that this looks random. And you can also kind of do the obvious thing. Let me erase it because
Who chooses those factor
these are random. AES chooses them. It's AES of 1, It's a.
It's yours.
But yeah, sure.
But yeah.
It exists. I mean, these things are not important in practice. It's just okay. And so now we can actually combine these two commitments into one. Because they each have like nice parts. In one commitment, you can commit to arbitrary size messages, and the other commitment you can commit to arbitrary long messages. But we can combine the two of them into one. And you know, we called it ABDLOP. And this is just so you have matrices A1. So basically, S2 is the randomness. And S1 and M are the messages. Okay, so without this part, this is the BDLOP commitment. Without the bottom row, it's the Ite commitment. So you can commit to S1 and M kind of. So when you want to commit to arbitrary size messages, you put them in here. When you want to commit to small but long messages, you put them in here.
You're saying I could simultaneously commit to both if I feel like it.
Yeah, and it saves you something because you don't have this top part twice, right? I can.
It's like a factor of 2.
It's a and it's all it's fine. Mm-hmm.
So
sorry.
So committing to M, isn't it essentially a regev encryption at the end of the day?
It looks like a regev encryption, except M is arbitrary size, so it's kind of maybe I don't know, maybe GSW. Shai says it's kind of a GSW, but I don't know. But yeah, this is you can think of it for certain values of B, and for a certain decryption thing, it's. But again, M is arbitrary, so that makes it a little bit. For GSW, you'd have to multiply M and like root Q times M or something like that.
Right.
Okay. Yeah. And so for this, you can also prove arbitrary over RQ, linear relations over RQ. So for example, if I want to prove R1S1 plus RM times M plus R equals 0, I can do that here as well. So the way I would do it is I would put the negative R1 here. I would put the RM here. And then this part, sorry, let me not do this. I would prove that A1 R negative R1 S1 plus A2 RMB S2 equals TA, and not important. I mean, if you understood the Ite thing, this is the same. This is just, you just have to work it out, and you will get, if you can prove knowledge of S1 and S2, then you prove that S1 and M satisfy this relationship. Okay, but it's just nothing interesting. Okay. All right. So we basically did this. So now something interesting is going to happen with this, right? Okay, so this we knew, I mean, or something like this was known for a while. Okay. So now what's the problem? Like, what if I want to prove a linear relation over ZQ, right? Like Vinod suggested, well, you can kind of probably embed some operation to RQ. But the problem is that if I prove an operation over RQ, right, then I'll end up proving quite a bit more than just over ZQ, because somehow the embedding will reveal more, because you also got to prove some product of polynomials, but that's going to reveal something else. Okay, so here's a fact. So suppose we want to do an inner product of R and S.
Over Z or
over Z, yeah. So now I'm going to define polynomials.
Can I ask a
Yeah.
basic question?
Uh-huh.
If I just embed it in a constant term, would that work if I just embed it in a constant term?
But how do you prove that? But what embed what? Sorry, the constant term.
You want to prove some value for ZQ, right?
Yeah.
Linear relation over ZQ.
Mm-hmm.
Can I just embed ZQ in the constant term of RQ?
ZQ in the constant, but how? So where do you embed the R and the S?
They're just gonna be in the constant term of different polynomials.
So now I have n different polynomials. Oh, that's terrible, right?
You mean that's the efficiency problem.
Yeah. Right now you just lost the fact. Now you just now need the number of polynomials times.
I said it's a basic question, but
Yeah. So that's the basic answer. It's terrible. Okay. That's all right. So let's say I define. So now given like two vectors R and S, I'm going to define polynomials R and S. Okay. And now what I claim is that this inner product is the constant coefficient of R times S.
We're knowing this is not a typo, yeah? You wrote them in different orders intentionally. The D minus one, the coefficients are decreasing in one and they're increasing.
Yeah. This would be a weird random mistake to make. This was quite intentional. Yeah. So now the claim is that the constant coefficient of this product is the inner product. Okay, so I'm embedding the coefficients, I'm sort of using all the polynomials, but just in the end result, the inner product. Okay, so is it something you believe or do you want to?
that's convolution, right?
It's a convolution, but there's a negative sign, so that's why there's
That's only
negative.
because it's x to the d+1, right?
Yeah, but you can do something. You can do some linear thing for almost any range.
Yeah.
Okay. All right. So the constant coefficient here is okay. Okay. So great. So now proving linear functions over Z is the same as proving the knowledge of a constant coefficient over R. So we can forget about this and just say, I want to prove the knowledge of a constant coefficient. Okay. So okay. So let's say the prover knows an M such that, and I'm going to use this notation to mean the constant coefficient. Okay, so there's some function over M, right? Some polynomial function over RQ now. Remember, we don't care about ZQ anymore. We care about RQ, but just the constant coefficient. So he knows an M such that the constant coefficient of a linear function is 0. Right, so this is the most general thing. And now what I'll do is I want to prove that I know it, right? Okay, so I create a commitment. I commit to M and some garbage term G. Okay, which will be defined later. And the point of G is to mask all the coefficients except the constant one. So G is going to be uniform, except it's going to be 0 in the constant coefficient. So G in RQ is uniform, except 0, except, let's use notation, G equals 0. So then the protocol will go like this. I send you C, the commitment. The verifier takes a gamma in ZQ, takes a random gamma in ZQ, sends the gamma. And what I would do is I send in the Z equals gamma times F of M plus G. Okay, so we'll keep and a proof that I actually did this correctly. Right? Notice that this is a linear function in M and G. And the proof that Z, so now I have a linear function over RQ. So I can use my proof over RQ that this equation is satisfied on the commitment of M and G. Okay? So he verifies the proof and checks that the constant coefficient of Z is 0. Okay, so it's fairly, yeah.
What if I choose G maliciously? What if I choose G to not have?
Yeah, In a non what?
If I choose G that doesn't have constant term 0, then
Well, that's what the challenge is for, right? So this gamma, right? If G does not have a constant term 0, right? So the point of this is that if this is not 0, if f of m is not 0, then for any G, constant coefficient of G, this is not going to be 0 except the probability 1 over q, right? So now we have soundness 1 over q for basically proving this guy. Okay, so but we have soundness 1 over q, and q is not so big. But it's okay, we can commit to many of these G's and have a bunch of gammas and do this. Another thing is, very importantly, if we have many functions f, right, the size of the proof will not go up. If we have many functions f, we just come up with many gammas and just do a linear combination of them, right?
Many coefficients. Is that what you're saying?
Yeah. So if we have many functions f, so if we have m such that f of I of m is 0, right? Then he would pick gamma 1 through, I don't know, gamma k. Right. And they would be sum of gamma I, fi of m plus g. Right. If any of them is non-zero, then only with probability 1 over q will you be able to get 0. Right. So this is actually quite important because we don't want that, because in going here, we're gonna be proving quite a few linear equations at once. Okay, so I think I won't have time for this, but yeah, maybe I'll just finish off this.
But wait, if you do this, isn't your soundness error still 1 over q?
1 over q, yeah. But now I'm proving many functions. But now, yeah, I'll have to do this I'll have to increase soundness. I will have to have a few G's, like maybe 4 G's or right. But to prove many functions at once, the proof doesn't increase.
So amortized, you're good.
Yeah, amortized are good, but yeah, to increase soundness. And this actually gets me back to why we want to use modulo LWE, right? So remember I said we want to pick D to be fairly small, right? So we want it to be big enough to have a good challenge space, but not too big. And the reason is because when we commit to these extra garbage terms, they go in, they are polynomials. We only care about the constant coefficient, but we have to commit to a polynomial, and this increases the size of our commit, even of z, right? Z is a polynomial. So the bigger the polynomial, it's just a waste. We only care about the constant coefficient, right? So you want to have as small as possible that fits a big enough challenge space. So this is why modulo of E is really the right problem to use. Okay, all right. So now we're here. Okay. So now proving linear relations over Z.
So
yeah.
So if your batch size is large enough, if your batch size, you're proving many statements. Yeah. Is as large as the ring LWE dimension, then you might as well use ring LWE, right? As opposed to module. I mean, is it?
No, because the size of the ring. This D is going to affect this Z. This Z is an element in here.
Right. So you don't want it to be too large.
No, right.
You don't want it to be too small either because of the challenge spaces.
Right.
C. Okay.
Good. So the right answer is like 64 or 120. This is the okay. Next, now let's try and prove linear relations over Z, right? Because once we have this, we can actually have something interesting. And okay, I won't show you how to do quadratic relations. But that's actually not so difficult. It's all right. So fact. All right. If let's say I have two just vectors, a vector S. So a vector S over ZQ to the D. Okay. Then an R is chosen from the following distribution. So it's chosen from, it's like -1, 0, 1. Let's say 0, 1, doesn't matter, with probability a half each. So R is chosen from 0, 1 to the D. Okay. If norm of S is large, then probability over R, RS mod Q is large, is greater than 1. So basically, if S has some large coefficient, it's not, you can't kill it off with it will show. This is a fairly easy thing to show. Okay. So now the idea for proving this is should be fairly straightforward given what we know, right? All the verifier has to do is give you a bunch of R's, and you somehow have to give him R times S. Prove that you actually did R times S correctly. We know how to do that because we know how to do relations over ZQ, and we know how to amortize them. So that's important because it's from 1/2. And so that will prove it. But there's a bit of a small issue. It reveals S, right? Okay. So the idea is kind of like this now, right? What you want to do is you want to pick a Y from some distribution, right? So you want to commit to, so you have a commitment to S. Now you pick some Y from this distribution and a bunch of garbage terms, right, that you need for this. So you have this commitment. And then the verifier, so you send this to him. The verifier sends you a bunch of vectors R 128, if you want 128-bit security, right? And what you do, so let's call this R. So he sends you a matrix R. You send him RS plus Y. And you do rejection sampling. Right? So you need a slight generalization of this. It's probability RS plus Y for all Y. You can also prove probability this is large is bigger than 1/2 if S is large. So there's no Y that can mask this S.
R is random mod Q, right?
Sorry?
R is random.
R is 0, 1. Okay. So then basically what he checks is that he checks that Z is small. We can give him the proof that everything is done correctly. He checks that Z is small. He checks that the proof works out. And now he's convinced that S was small, right? Because we proved to him that Z really is R times S plus 1.
You have to choose Y to be like small, but not too small or something.
Exactly. It's exactly the same things as over here, right? It can be small, but not too small. And so now what this proves is something better than what we could get here. We basically proved that we know okay, so now we haven't done the main thing. And if you, in addition, want to prove this, well, that's just another linear equation. That's just another set of linear equations. So you also can prove that S satisfies this. Okay, so now you've just proved that S is small, S satisfies this, and kind of that's it, right? So you end up proving that A times something that's bigger than your original S because of this is T. But so we got rid of the C. Okay.
So for the whole thing, you just used the ability to prove linear relations over the quadratic. We haven't
seen it yet. But once you can do quadratic, right? So actually, the quadratic, there's not much. I mean, it's just kind of, but this was known before. Once you can do quadratic, you can see that you can prove the norm, right? You can prove the norm of S is small, but you're proving that the norm of S is small mod Q, which is not really the same as the norm is small, right? So what you have to do then is prove that, so you end up proving that you can prove with the quadratic that the norm of S squared is like some B, okay, mod Q. But, you could have had a wraparound. So what you have to prove is an approximate you have to prove this part first, right? So if you prove that, hey, actually S is small, you will not get a wraparound, okay? And the norm of S squared is B mod Q, well, there's no wraparound. So that means norm of S really is B. So basically you use an approximate proof to show there's no wraparound, and then you prove relations mod Q. Okay, so this is the strategy for proving this. And yeah, of course, once I do this, there's a somewhat nice part of the fact that this multiplication, you know, what Noah said I wrote in the backward order, it's actually an automorphism in this ring. So in some sense, you will not have to send both. Okay, because I'm gonna, you know, if I want S, I want to send commit to S and commit to, if I want to do the product, I can commit to S and commit to this automorphism of S. But because it's an automorphism, I don't have to commit to it. He can compute it himself. Right. So this is like a nice part. So it saves you another like, sort of small factor in the thing. But otherwise, you could use any ring and just commit to S and commit to the weird permutation of S, whatever weird permutation it has to be. And then just prove that you did the permutation correct. Okay, so this is kind of, so the kind of the takeaway is the way to do commit and prove protocols is you have your commitment scheme, you commit using this commitment scheme. You can prove, you have to use the fact that polynomial products in the first code, appropriate polynomial products give you vector products, give vector inner products. Then very importantly, you can prove that S is kind of small using this. Right, and actually, like in the L2 norm, it's even nicer because you can get a really tight bound using the Johnson-Lindenstrauss, but that sort of doesn't matter so much for this high-level thing. And then once you know that S is small, you can prove quadratic relations mod Q, and that implies quadratic relations over Z. Over ZQ implies over Z. So that's the high-level thing, and then with this, you basically get you get proofs that are fairly small, that are only between 10 and 20 kilobytes for many useful things, like proof of correct encryption. You can get ring signatures. You can get one or many proofs. You can get sort of all this linear space proofs. You can get only a little bit more expensive than just the commitment. Just having a commitment and proving you know the opening to a commitment. All thanks to the fact that all these garbage terms, you know, that have to mask stuff are actually small because they live in this small ring. Okay, so this is quite kind of important. Instead of in ring LWE, this D would be 1,000 or 2,000, whereas modulo LWE, it's really just 64 or 128. Okay, so that really is the right problem to use. And yeah, I guess not much else.
So we have a shorter lunch break. It's time for one short.
If you want to do batch proofs of correctness of many commitments, right? That many encryptions are 0 or whatever, you know, with the proof size that is independent of the batch size.
So the question, but the commitment would grow, right? So if you don't count the commitment size.
No, so I guess by definition, you would have to come up with a shrinking commitment.
But you said they're encryptions, right? So if they're encryptions, you probably can't shrink them.
No. What I mean is the statements there are end statements.
Okay.
Right?
Yeah.
They're there. We can't do anything about it. That's the way it is. There are end witnesses too. They're there too. But somehow I could, you know.
So this is this is you want to snark, right, from lattices, and
it's not a snark really. It's a batch argument.
So, okay. So here's something you can do. It's not, but I mean a snark would solve that. So here's something you can do, right? Let's say I have A times S1 equals T1, A times SK equals T4. It's something that's known, okay? I can prove to you in a fairly short thing that that for all I, A times this zi equals t times c.
Right.
So this I can do, and it's short.
Well, that's great. So with proof length independent of k, right?
Yeah, I mean, if k is not too big, it grows linear. The coefficients grow linearly in k. Okay, so but this is something that's already known, right? But this is not quite what we know. We can't. It wasn't known how to get rid of this. It wasn't. Yeah, but this is something you can do. Yeah. So it's not quite but I think a snark would solve this. Yeah.
I know,
Better, but
yeah, okay.
Yeah. So I think one should aim towards this and this. Yeah. And the way you do this is very simple. You just do a sum of SI CIs here plus one.
Right. Yeah. Thanks.
Two.
Short lunch break.